Imagine you are diving into the world of econometrics and statistic modeling. Picture this, you are examining a regression model trying to make a sense of relationship between variables. But suddenly you encounter a stumbling block known as heteroscedasticity. Heteroscedasticity within this context refers to the uneven variability or unequal dispersion of errors or residual across different levels of independent variable within a regression model. Essentially, it means that the spread or a variance of these residuals is not constant throughout the range of predicted values. This inconsistency contradicts a fundamental assumption in regression analysis called homoscedasticity, where we expect the error variance to remain steady. Deducting heteroscedasticity involves into residual plots or using a statistical test like a bronze pagan or a white test. Understanding and addressing heteroscedasticity became a crucial here. Its presence can skew statistical inference, leading to biased estimation and impacting the reliability of conclusion drawn from the regression analysis. Heteroscedasticity versus homoscedasticity. Starting with heteroscedasticity, variance of residual vary across the independent variable levels, resulting in uneven scatter around the regression line, violating the assumption of constant error variance and potentially causing biased standard errors and inefficient parameter estimates. Such variance inconsistency compromises statistical test reliability, affecting the precision and accuracy of regression analysis. Homoscedasticity denotes a uniform spread of residuals around the regression line, maintaining a consistent variance of errors across diverse level of independent variable. This uniform variance signifies a stable and dependable variability in the model's errors, crucial for reliable statistical inference.
I am Gulabshan and I will be discussing the causes of heteroscedasticity. As in this graph, we can see as the vertical distance between residual and predicted value increases, there is an implication of presence of heteroscedasticity. The sources of heteroscedasticity being one, incorrect functional form and the wrong data transformations. Second, improvements in data collection, wherein the procurement of data is the methodologies differ and that can be different according to institutions. Third, being model specification errors, wherein wrong models or important variables are omitted. As we can see in the graph where country versus stock prices plotted, Chile being the outlier, which significantly affect any insight derived from this graph. And the second cause being uneven distributor of regresses, skewness in the distribution of variables included in the model. The effects being biased f-test, as f-test automatically assumes the homoscedasticity, and in case of heteroscedasticity can it lead to incorrect conclusions, and incorrect confidence in intervals implies that there is either a very narrow or broad corridor of values which are very much apart from the original values.
OLS estimation in the presence of heteroscedasticity contains model assumptions where classical model introduces the heteroscedasticity to variable regression model is yi is equal to beta 1 plus beta 2 xi plus ui, and OLS eliminator of beta 2 square cap is summation of xi yi divided by summation of xi square, where variance of OLS estimator beta 2 is sigma I square upon summation of xi, which is different from heteroscedasticity. And then we have best linear unbiased estimator, which remains unbiased and consistent despite heteroscedasticity, and unbiased does not depend on the variance of mu. Efficiency and best estimator, despite being unbiased and consistent, beta 2 square is no longer blue in the presence of heteroscedasticity. We have GLS, whereas which means that elimination method is designed to address heteroscedasticity in data by consisting different ways to observe observations based upon their variability, and by approaching this enhances the efficiency of eliminating the population regression function PRF by explicitly considering the unequal variability of the dependent variables. When heterostatic variances, GLS transforms the original regression model to create a version with homoscedastic errors, which ultimately goal is to enhance the precision of estimating relationships while addressing issues related to varying variances in the data. Now we have variance of beta 2 square equation, which is 1 upon summation of wi x I star square. Difference between OLS and GLS. In GLS, we minimize the weighted sum of square residuals where weights Wi are 1 upon sigma I square. Contrastly, OLS minimizes an unweighted or equally weighted sum of squared residuals. The weight in GLS are inversely proportional to sigma I, meaning that observations from the population from a large sigma I receive smaller weights and vice versa in this process.
Consequences of heteroscedasticity in OLS estimation. When using OLS with heteroscedasticity, confidence intervals may be unnecessarily large. T and F test can yield inaccurate results due to an overlarge variance of beta 2 cap. OLS can be biased in the presence of heteroscedasticity, affecting the reliability of confidence interval and hypothesis testing.
Detection methods. Before we start, I would like you to pause this video and go through this example quickly. Detection methods. Park test. It involves a regression of the logarithms of the absolute residuals against the logarithm of an independent variable suspected of causing heteroscedasticity, such as housing price. A statistically significant coefficient in this log-log regression indicates heteroscedastic variance. You would perform a regression of the absolute values of the residuals from your original house pricing model against the independent variable. A significant relationship in this regression indicates heteroscedasticity. Second, Glitzer test. In this test, we regress the absolute residuals on transformed values of the independent variables, like square roots, logarithms, or reciprocals, to identify specific patterns of heteroscedasticity. Significant coefficients in this regression point to heteroscedasticity tied to the level of the independent variable. Similar to the Park test, but instead of using the absolute values of the residuals, you might use transformations of the independent variables and look for a significant relationships. Example, the square root of the house size. Third, Spearman's rank correlation. This non-parametric method involves assessing the correlation between the ranks of the absolute residuals and the ranks of an independent variable. A high Spearman rank correlation would indicate a systematic increase in variance alongside the independent variable, signifying heteroscedasticity. A high correlation would suggest that as the house prices increase, so does the variability in pricing errors, indicating heteroscedasticity. Informal detection methods. First, nature of the problem. Informally, we start by recognizing scenarios prone to heteroscedasticity, like in real estate where larger, more luxurious homes often display greater variability in prices. In this context, the nature of the problem is evident as we expect larger, more expensive houses to have a wider range of prices due to factors like design, amenities, and locations. Second, graphical methods. Visually, we use scatter plots of residuals versus predicted values. A clear pattern such as funnel shape where variance increases with house size visually confirms heteroscedasticity. A scatter plot of residuals against predicted prices will likely show a pattern where variance increases with size or price of the house. This funnel shaped pattern in this plot is a classic design of heteroscedasticity.
Remedial measures of heteroscedasticity. Heteroscedasticity does not affect unbiasedness and consistency of OLS estimators but makes them inefficient. There are two approaches for remediations. Variance is known. When variance is known, correct heteroscedasticity using WLS for blue estimators. When variance is unknown, White's method provides consistent estimates of variance and covariance of OLS estimators. White's heteroscedasticity corrected standard errors are also known as robust standard errors. White's standard errors are larger than OLS standard errors. Estimated t-values are smaller, which makes them significant. There is also another method called possible assumption about heteroscedasticity pattern. In summary, heteroscedasticity refers to a situation where the variance of residuals is unequal over a range, which let the analysis be invalid.